This third video in the series on Unity's GraphToolkit version 0.4 will focus on building the runtime graph, including a topological sorting of the graph. First, an overview of what is being covered in the video. These nodes are editor time nodes. We'll build a one-to-one correspondence with them to the runtime nodes. LayeredNMIporter is the class that does all the work. So it's got a couple of variables needed to handle this. Ordered nodes, which is a list of all the nodes in the order they should be executed. Blackboard variables, which is a list of runtime variables from the Blackboard. The result map runtime node, which is the root node for the topological sorting. And there's the LayerNMRuntimeGraph. This holds a node list with the runtime graph, the Blackboard variables, the runtime variables, and a graph context, which is information needed to execute a runtime graph. These runtime variables are very simple. There is a name, there is a variable kind, which isn't implemented. It's used for subgraphs in case you need to link a subgraph inside a graph, which I'm not handling. The data type, which is saved as a string because it doesn't serialize in the inspector with Unity. And then an int_val or float_val or float array as map to store the actual value of the variable. And then back to here. We see that this is using the Unity Editor namespace, but at runtime we can't use Unity Editor classes. So we have this dict node ID, which takes an editor type node and matches it to an integer. And then we have an integer which goes to the LayeredNMRuntimeNode node dictionary. So we don't have to reference editor nodes at runtime. These are for handling variable types. They are used for testing if a variable is an int, a float, or a float array map. The onImport method takes a context and does the work of converting an editor graph to a runtime graph. Here we assign the values for type string testing. Load the graph. If the graph is null, then it failed to load and we can log an error. The other type of error to handle is when the graph editor found an error and saved it to error message. Create a LayredNMRuntimeGraph. Set its error message values and concatenate the messages together for easier displaying in the inspector. Add this LayredNMRuntimeGraph to the context and set it as the main object for the asset. We log that we found an error and return. We make the runtime version of the Blackboard variables. We take an editor graph as an input. We iterate over all the variables in it. We add a new runtime variable to Blackboard variables. Assign the name, the kind is not implemented, and the data type. Next we fill the dict node to ID dictionary with an int assigned to each editor graph node. Now we make a runtime node for each editor graph node and get the root node for the graph. Setport takes in an inode and a layered runtime node and sets all the ports on the runtime node. First we deal with the imports. go through all the imports, make a runtime port, set import to true, and set the name. We get all the connected ports from import. If there are connected ports, we go through each one and get the node. If the connected node is a constant, we go down through here, assign the import data type. We try to get the value from the constant node and assign it to the runtime port. For a float value or for a map type two-dimensional float. And if none of those happened, we would log an error. That would only occur if you'd added more types of ports, but I hadn't updated this code. If it's not a constant node, we make a linked port. We assign the port name and the ID which we get from the dictionary for this connected node. And then we add it to the list of linked ports. The other case is if this is empty. In that case, we just directly assign the value from the runtime port to the in port. The value can be seen here. And this code can also cause an error if your code has not been updated after adding more types. And then you add the runtime port to the node. Now for outports, it's a bit simpler. We make a new runtime node. It's not an import, it's got a name. We make connected ports. We assign the connected ports. We go through all the connected ports. We make a new port. We give it a name. We give it an ID code. We add it to the linked ports. We add runtime outports. And then for the result, we return the runtime node. And then that brings us back up to here. Assign the variable node to the variable runtime node. We give it a name. And then we add a new dictionary entry for this ID that matches the editor node ID. And then we do the same thing, but this time we're not doing variable nodes. Note this continue. So we would have gone to the next editor node. Now for the LayeredNM node case. We do the translate node, which is slightly different. The difference being that we don't do the data type setting, but we do make a new runtime node. SetOptions is only for non-I variable nodes. We have two types of options in this graph, a drop-down of noise map types and an integer for the number of imports. Setting options is fairly simple because we don't care about the dynamic port options, as dynamic port count is only used to create the correct number of ports in the editor node, and that's already been done. So at runtime, these ports are already going to be in the editor node, and we don't care about this value. We do care about it here in the standard generator node, because it tells us the type of noise, and we have to make sure that value gets passed over to the runtime node. So iterate over all the options. There's only one in this graph, but in general there could be more. We make a runtime option, which is just a name for debugging, and the int value of the option. So the name we set to the name. If the data type is height map type, it means this is a standard generator node. So do we try and get the value and assign it to val, then assign val to int val. We add the option to the runtime node. We assign the node ID and return the runtime node. If it's the result map runtime node, we know that there's only going to be one, and we assign it to the result so that we can return it later. Now we add the node to the dictionary. When we have processed all the nodes, we return the result. Now we're back up here, so if there was no result map node assigned, that's an error and we log it. It shouldn't be possible to get this because when creating the editor graph, we should have produced an error if there was no result map node. Then we just make a list of all the nodes. This is because we're going to make out node IDs. Out nodes are very simple. They're just a hash set of int IDs of nodes linked to an out port, and they are attached to each node for use in the topological sort. This hash set will be modified, so we don't want to just use our list of out ports. So all we do is find all the out ports by being everything that is not an import. We find the linked port node and get its node ID. For example, for this standard node, if this was node 4 and 3 and 5, we would put the numbers 4, 3, and 5. Sorry, I just spilled the marketing graphics on the video. While they dry, if you are enjoying this content, please leave a like. If you would like to see more videos like this, please subscribe. If you have any questions, suggestions, or spot a mistake, please leave a comment or join the Discord. The link is in the description, and comment there. If you need some Unity programming for an indie project, contact me at the link in the description. 10% discount on programming services if you mention this YouTube channel. And now we come to the meat of this code, and that is the topological sort. We're going to do it in 2 stages. First, we get rid of all the nodes that don't contribute to reaching the result map. So this node contributes, and this node does. But these two end up in a dead end, and they don't contribute to the result node. So we want to eliminate them. We start up here. We go into the topological sort. Note that we've set it to false and false for the include root and save order. There is a link to the topological sort algorithm on Geeks for Geeks in the description. So if save order is true, we clear the ordered nodes. If we're not doing save order, we're not going to do anything to the nodes. So first we make our result, which is going to be all the graph nodes passed into the method. Then we find zeros. So zeros are nodes with 0 out nodes. So that's going to be the result map node and the sum node. But we check if we're including the root. We're not including the root, so we are going to remove the root node, which is the result map node. So we're going to remove it from 0, so 0 consists of just the sum node. If we're doing save order, we save all the zeros. We're not doing save order. Remove all nodes and zeros from result. So sum node is removed. Then for each node in result, from that node's out nodes, remove any ID that matches a 0 node ID. So we move down here and see that the 2 standard generator nodes have had the sum node ID removed from their out node IDs, and so are no longer linked to sum node by out node IDs. We find all nodes with 0 node IDs. That's these 2. There's a standard generator node and a result map node. Result map node gets excluded because we're not including the root node. Next iteration. This standard generator node is now in zeros. we go through again. We remove the standard generator node and this link. And now when we go through, we're only going to find 1, 0, the result map node. That one will get removed at the bottom of the loop. So when we get here, we won't have any zeros, and we return result. So result consists of these 4 nodes and not these 2 which we removed. So 4 nodes end up in pruned. So we come back up here. Pruned node consists of this set without these 2. And we do a topological sort again. But this time we're going to include the root node and we're going to fill ordered nodes. So this time when we go through, it's all the same code. We clear ordered nodes since saved order is true. We keep the result map node since include root node is true. We save the zeros to ordered nodes. We cut this link in out nodes. Next iteration. Now this sum node is added to zeros. We cut these 2 links. We add sum node to the ordered nodes and move down again. This time adding island node to ordered nodes. Finally, we add this last node to ordered nodes. Nodes were added in the order 1, 2, 3, 4. And then we pop back out. So now this is the order 1, 2, 3, 4. But this is the reverse order of what we want. We want to execute this one first, so its result can be used in these 2. And then execute island node, so its result can be used by sum node, in turn used by the result map node. So we reverse this order. And then we come down to the save. This is similar to the save when we have an error. We create a runtime graph. This time we put ordered nodes into node list, and the Blackboard variables into the Blackboard variables. We put this whole runtime asset into the context and call it runtime asset. Set this to be the main object. Context gets passed up to the caller of this method, which adds it to the graph asset. And now we look at LayeredNMRuntimeGraph. All the code except node list and Blackboard variables is only used when executing the graph. This will be covered in the next video. The remaining runtime node and variable code is either overriding toString or debug name to return a more detailed string, or involves graph execution code. Graph execution code is covered in the next video. The next video will cover executing this graph at runtime, scriptable objects, and this mono behavior. The scriptable object will convert height maps into meshes. And that's it for this video. Thanks for watching to the end.